Hi, everyone. Thanks so much for listening. My name is Agi Villanyi I'm from MIT, and this is Classical Commitments to Quantum States. And it's joint work with Sam Gunn from UC Berkeley and Yal Tauman Kalai from MIT and Anand Natarajan from MIT. So let's begin by recalling bit commitments in the classical setting. So a classical bit commitment is just a two-party protocol between a sender and a receiver. And it consists of two phases, the commit phase and the open phase. And the idea is that between the commit and open phase, there's this sort of digital lockbox that is shared between the sender and receiver. So let's go into a bit more detail. So to commit to a bit B, the sender applies some commitment algorithm to B to get the commitment string Y. And then in the open phase, to open this string Y, the sender sends the opening string Z, and then the receiver just runs some checks on its side to make sure that it was actually a valid opening and that it's not interacting with some sort of malicious sender. Okay, so we need a few properties to actually make such a protocol formal. The first property is what we call correctness. And this is a property for the scenario where both of the parties are honest. So we say that a protocol is correct if both parties are honest, then the receiver learns the bit B by the end of the open phase. Binding is a property in the case where you have a malicious sender. So it says informally that basically the sender can't change its mind. More formally, the way to state this is that there's no sender that can open a commitment Y to both a bit B and its complement, 1 minus B. And then finally, we also have hiding, which is a property against a malicious receiver. So it says that there's no receiver that can guess the bit B with probability better than 1/2 before the open phase. So it's truly hidden while it's in this shared lockbox state. All right, so in the quantum setting, there's a very natural question to ask, which is, how do we commit to a qubit? And this was addressed a couple of years ago by Gunn, Ju, Ma, and Zandri in the context of having both parties being quantum, so quantum sender and quantum receiver. But in this work, we address the case where you have a quantum sender but a classical receiver. And this is a totally new setting. All right, so how would we even begin to think about how to formalize such a protocol in this setting? So you have a sender that is in BQP and a receiver that is in BPP. Well, the first place to start is to think about how we would define the properties that formalize a commitment scheme. So first property, which is correctness, how could a classical receiver receive a quantum state psi if the communication between the two parties is purely classical? Well, the way we choose to define this is to send measurements of the state psi. And so formally, what we would want is that after the open phase, the sender helps the receiver learn some outcome of a measurement of psi in a basis S. And so whatever the receiver gets at the end of the open phase should match having just measured the initial state psi in that basis, so in either the standard or Hadamard basis. Okay, so the next property, binding. How can a receiver ensure that the sender stays committed to a specified quantum distribution? So this is different than the classical setting because there's an asymmetry between the classical honest party, which is the receiver, which is just in BPP, and the potentially malicious sender, which is in BQP. So this makes this much harder to do in the quantum setting than just in the classical one. And we formalize this using two properties. The first one you can think of as just being a quantum analog of the classical property that the sender doesn't change its mind. So what we want to say is that for any two opening algorithms, the opening distributions generated by the sender are computationally indistinguishable. But then we also have a second property, which is unique to the quantum setting, which says that there's some efficient procedure that extracts a quantum state from the sender. And this property doesn't exist in the classical analog, but it may seem familiar from prior works, which we will get into later on. Okay, and then finally hiding. So how do we make sure that the receiver cannot guess the commitment? Well, this one's actually quite easy because we can just apply any classical commitment scheme that is hiding to the commitment string Y. And because the sender's measurements are random in the case where it is an honest sender, it'll always be kind of implicitly hidden from the receiver. Okay, so let's get into our first result, which is a single qubit commitment scheme. And the syntax of this follows fairly directly from the classical analog. So we have just the algorithms gen, commit, open, and then the verification algorithms, which we split off into two algorithms, ver and out. So let's just go through it. So first, the receiver chooses some public and secret key, and then sends over the public key to the sender. The sender then has some quantum state psi that it would like to commit to, so it applies its commitment algorithm, generates some post-commitment state psi commit, and then the commitment string Y. And then it sends Y back to the receiver over the classical communication channel. And then in the open phase, the receiver selects a basis S, that is either the standard or Hadamard basis, and then sends that over to the sender, and the sender then opens its quantum state in that basis. And then it generates some opening string Z, which is then sent back to the receiver. And the receiver then does its checks on its side to make sure that there was no cheating going on the sender's end. So our construction for this follows from a previous work, which we will get into later on. But first, I will go over our other results and applications. And our main application is succinctness. So we have a multi-qubit commitment scheme that is binding in both the standard and Hadamard bases, but we also have a succinct multi-qubit commitment scheme, which means that you can commit to some L qubit quantum state using only a polynomial in the security parameter number of classical bits. So it's independent from the actual length of the starting state that you're committing to. And this is really nice because we can directly take a quantum analog of a very famous classical result, which is that you can take commitments to create succinct arguments for NP. So in the quantum setting, this would be succinct arguments for QMA, and this was achieved using non-standard cryptographic assumptions, so IO, a couple of years ago. But what we do is we give the first succinct interactive argument for QMA that is under standard graphic cryptographic assumptions, and specifically under LWE. Concurrently, there was also work that did this by Mecker, Natarajan, and Zhang, but their protocol is actually based on non-local games, and it's substantially different from ours in its syntax and everything. Okay, so now let's get into the measurement protocol, which is what our construction uses as a starting point. So the measurement protocol was developed by Mahadev in 2018, and it was used for verifying quantum computations. And it's based on this primitive called trapdoor Claffey functions, which for the purposes of this talk, you can just think of these functions as being such that if you have some image Y, it is hard to invert Y to some pair of preimages without access to some secret key or a trapdoor. And this is what allows the receiver to have leverage over the sender, even though it's computationally weaker. Okay, so the measurement protocol works by the receiver first generates a public key and then sends it over to the sender. And the sender then again has some quantum state psi, and it commits to psi using its commitment procedure. But what the commitment procedure does is it entangles the initial state psi with a pair of preimages. And this procedure also generates an image Y, and that is what is sent over to the receiver as the commitment string. And then in the open phase, the receiver chooses a bit S that corresponds to either standard or Hadamard basis, and then the sender measures psi commit in that basis to get the opening string Z. Opening string is sent back to the receiver. And then, so if it was a standard basis opening, then the receiver can just parse the opening string directly and perform a consistency check because it has the image Y that it got in the commitment phase. And then it'll just output the initial bit of Z if this was correct. Otherwise, it'll just reject. In the Hadamard case, though, it doesn't perform any checks, and it has to do this decoding procedure that sort of falls out of the crypto, but there's not actually any sort of consistency check with the commitment phase. And we'll see in a moment why this is important. So this is a correct scheme. It follows directly from calculation. You can check out the original paper, but it's not at all binding in the Hadamard basis. So it's fully binding in the standard basis, but it's not binding in the Hadamard basis. And this is important because you could imagine that this directly should give you a commitment scheme like we had outlined earlier, but it doesn't for exactly this reason. So let's go into this in a bit more detail. So let's say we're committing to the plus state. We generate this, we entangle the plus state with this pre-image pair, but then the sender can very easily just apply poly Z to the first qubit, and this adds a phase error to the committed state. So the sender has successfully cheated, but there's no checks done on the receiver's end that catch for this. And so this is actually a way that the sender can very easily break binding, even this simple example. So how do we fix this? Well, we simply apply the measurement protocol twice. And the intuition here is kind of similar to the short code, where you're concatenating a bit flip error with a phase flip error to protect for both kinds of errors. And that's exactly what we're doing in this protocol, except in the cryptographic setting. Okay, so let's get more into our construction just for single qubits. So the beginning of the construction is, we're all already experts. So we have some public secret key generated that's sent over to the sender. And the sender then applies this first layer of the Mhadev commitment, and it's entangled over a pre-image pair with some image Y0 that's generated. But then we perform a basis change. So we move from this computational basis to the Hadamard basis by just applying Hadamards to each qubit of the post-commitment state of the initial layer. And then we apply the Mhadev commitment again. So now each bit of the resulting basis change is entangled with some preimage. And this generates a new set of images. And now the entire commitment string consists of the initial image together with the next n+1 images that come out of the second layer of the commitment. And then to open, we simply just measure each qubit to open in some basis S, we measure each qubit in the basis 1 minus S and then perform the necessary checks. So because we do this basis change, we actually have to measure in the complement of whatever opening was requested. Okay, so how do we generalize this to the multi-qubit setting? Well, to commit to an L-qubit quantum state, we can actually just generate L public keys and then apply the single commitment scheme qubit by qubit. But you might notice that this already uses at least L bits of information to commit. So this is in no way succinct, which we will address in a moment. But to open, the receiver sends L basis openings, requests L basis openings to the sender, and then the sender will measure each qubit of the committed register in that corresponding basis. Okay, so how do we make this succinct? Well, the first thing we can do is make it semi-succinct, which that just means that the receiver's messages are short, but the sender's responses can still be long. So what we do is we generate a single public key, PK, and then commit to each qubit of the initial state psi by just reusing that public key. And this now eliminates the issue where we're already using at least L bits of information to commit to quantum state. But we have a new issue, which is this problem of leakage. So in the original protocol, there's the problem where the sender can easily cheat by choosing choosing a string D so that it can learn the secret key from the receiver's checks that it does on its side. And in the MODIV protocol, this is prevented by using what is called the adaptive hardcore bit. But the problem is that this doesn't actually hold if the key is reused, because in this case, the general intuition is that the receiver has access to, the sender has access to more information. And so in the original protocol, you actually have to generate these independent public keys on each round to make sure that this attack doesn't happen. So we need to address this, which we will. But assuming that we can address this, we can just follow the standard semi-succinct to fully succinct template from previous work that uses these post-quantum interactive arguments of knowledge. So really, the difficult part was showing that we don't actually have leakage in our setting. Okay, so how do we actually do this? Well, the desired property is that opening the ith qubit still seems sufficiently random, even if you have openings to the previous I-1 qubits. And to argue that this is the case, we show that because we have checks in both the standard and Hadamard bases in our protocol, we have this strong binding property. And we argue that with this strong binding property, the sender's responses look sufficiently random. And this, together with a sort of a modification of the adaptive hardcore bit, which we call the distributional strong adaptive hardcore bit, these together guarantee that the decodings done on the receiver side don't actually reveal any information about the secret key. And so the leakage is totally benign. And okay. So let's just do a quick overview of the analysis. So the correctness follows from their calculation, but binding was fairly difficult to show. So for the first binding condition, we actually rely on this property called the collapsing property of the Trapto-Claffey function family. And that basically just says that you can't distinguish a preimage from a measurement of it. And so we say that if you could have two opening algorithms that are distinguishable, then you could also break this collapsing property. And for the second binding condition, which is that you can extract a quantum state from the sender, we use the standard swap isometry, and then together with this, with how we handle the leakage, we argue that you can apply that isometry directly. And really the challenge there is to show that the measurement operators that are applied in the protocol anti-commute. And that's why we need to make sure that there's not actually any leakage. Okay, so we give the first formal classical commitment to quantum state scheme. There's a few interesting open questions. So our binding definition actually assumes that you have senders that are accepted with high probability. And so to achieve this, we need to repeat the protocol many times sequentially. So an open question is, can this be improved? And a second open question is, can we construct commitment schemes out of more minimal assumptions? So this is also related to a big open question in verifying quantum computations, which is, can you do this information theoretically? So I don't believe that you could have such a commitment scheme that is information theoretic, but could we do it out of LPN or something that is lighter weight than LWE? And are there other applications for commitment schemes that perhaps do not have classical analogs? So we addressed succinct arguments for QMA, but maybe there's other applications that we didn't think of. And then finally, can we construct a publicly verifiable classical commitment scheme? And that is all. Thank you.
I think you're good with the times.
Okay, nice.
It's a bit over.
Yeah. Okay. I can stop the
I guess you